Hi everybody, I'm going to present FreezeML, for which we have designed this very beautiful and definitely in no way cheesy logo. Now, our motivation for FreezeML was to design a simple way of integrating first-class polymorphism into ML, and as we'll see in a minute, we really only needed to add two things to ML to make this possible. And this is joint work with Sam Lindley, Jan Stodorek, James Cheney and Jonathan Coates. I want to get started by discussing the general idea of combining ML and first-class polymorphism, or rather combining ML and SystemF, because that's a prominent language that supports first-class polymorphism. So let's get started by revisiting the differences between the two languages. If you look at ML here on the left, it supports only prenex polymorphism. That means it's perfectly possible to type the polymorphic identity function, which has the type for all types A to A. But quantifiers can only occur at the top level of a type. This is different in SystemF here on the right, because it supports rank n types. That means quantifiers can occur arbitrarily nested inside of types, rather than just at the top level. In ML you can only instantiate type variables with monomorphic types, which means types that don't contain any quantifiers at all, for example int here. And on the other hand, in first-class polymorphism you have polymorphic instantiation, which means that you can instantiate type variables with polymorphic types. ML supports type inference, which means you never have to write any type annotations if you don't want to, but type inference is undecidable for SystemF, which means that you have to fully annotate SystemF programs with their types. In ML, let bindings implicitly generalize the let bound terms. For example, if you write let id be defined as lambda x.x, then this lambda term is implicitly generalized and id gets the polymorphic type that we had at the top of the slide here. And in SystemF, on the other hand, you need to write explicit type abstractions. So this big lambda a dot something here means please generalize over a, and then a is bound in the body of the type abstraction. In ML, variables are implicitly instantiated, which means we can apply id to 3 directly, and its polymorphic type will be instantiated automatically. And in SystemF, we need to apply id to int first in order to explicitly tell the system how to instantiate the polymorphic type, and only then can we apply the result to 3. And finally, the order of quantifiers is irrelevant in ML, but it's important in SystemF. So we have two types here that are the same, except that we quantified over A and B in different orders. And in ML, those are the same type, but in SystemF, they are different types. Let's have a look at the landscape that FreezeML lives in. Actually, there's a whole alphabet soup of systems that combine first-class polymorphism with other language features, most notably some degree of type inference. A lot of bright minds have worked on this, and I wanted to show some of them here, but this kind of accidentally turned into something that looks like a Zoom call. There isn't really a consensus about how the ideal design should look like, which is why there are so many of these systems. They all make different trade-offs, so let's look at one example question these systems face. We use the function single with type for all a to list of a, so the square brackets are the type constructor for lists here. And id is the identity function that we've seen earlier. Now what should happen if you apply single to id? Should we instantiate id? In that case the result type is list of c to c, where c is some arbitrary type. Or we could keep id polymorphic, in which case we end up with list of for all b to b. Of course, if this application was to occur as part of some larger expression, the context may give you clues about how to type this. And many systems do this, which means that they have heuristics built into their type systems that in many cases will do just the right thing. But in FreezeML we've taken a different approach, and let's have a look at that next. For FreezeML we had several design goals, and here are 4 of them. We wanted full first-class polymorphism, meaning that we are able to embed SystemF into FreezeML. Secondly, we wanted to use just perfectly standard SystemF types and nothing else. And most importantly, we wanted to design a simple system that values simplicity over parsimony. So we wanted to design a system that is very easy to understand and implement, rather than one that tries to be very clever in order to save you some ink. This is also reflected in our desire for predictable behavior, meaning that it shouldn't be difficult to look at a piece of code and know exactly what the typing will look like. And as it turns out, we were able to do that and get a conservative extension of ML by adding just 2 things. A freezing operator, which prevents the implicit instantiation that ML does, and type annotations on let bindings and lambdas, which you will need sometimes. So here's what we've taken from ML. We kept the implicit instantiation of variables that ML does, and we kept the let generalization. FreezeML also obeys the value restriction, but that won't really be relevant for the rest of the talk. And finally, we still have type inference, but with some terms and conditions attached about when you need to annotate binders with types. What we've taken from systemf are its types and its first-class polymorphism. And because we are using exactly systemf types, the order of quantifiers matters in FreezeML. Finally, we do have operators for explicit instantiation and generalization in the language, but we will see in a moment that those are actually just definable as syntactic sugar. I'll show you how FreezeML works by going through some examples. We will start with looking at how FreezeML handles the single apply to ID example I showed a minute ago. The rule is simple: every variable is always instantiated. That means that FreezeML just behaves like a syntax-directed presentation of ML, if you're familiar with that. In our example, this means that the type of single ID is list of C to C, where C is some fixed type. Now let's look at the freezing operator. If we freeze a variable, it is not instantiated, so single apply to frozen ID will preserve the polymorphism of ID. And then we get list of for all b to b. So this means in FreezeML this decision of whether to instantiate or not is left to the programmer, rather than the type system having some heuristic built in for that. One thing to mention is that of course single is still implicitly instantiated here, but the interesting point is that we instantiate the a in single's type polymorphically with for all b to b. So the implicit instantiation of variables that I mentioned earlier is always allowed to instantiate polymorphically. And of course, that isn't the case in ML. Let's look at functions rather than variables. If we apply single to lambda implementing the identity function directly, we again behave just like syntax-directed ML. This means there is no implicit generalization here, because the only generalization that ever occurs is when we use let bindings. So what if we do want to generalize this lambda? As I said, the only way to do that is by writing a let binding. So if we let bind this lambda to some temporary variable and then return that variable frozen, we get a generalized version of the lambda, and the freezing preserves the polymorphism. Now writing such a let binding every time you want to generalize something is rather verbose, but in fact this generalization trick works for any term that you want to generalize. And that's why we added it as an operator. So $$ is the generalization operator. But it's actually just syntactic sugar for a let binding that then freezes the result, just as we just did. And don't get confused here, our $ operator has nothing to do with Haskell's $. Operator. Let's look at some more examples, and here we'll be using the typical head function that takes the first element of a list. And we assume that there's a variable IDs with type list of for all a to a. So that's a list of identity functions. That's a pretty boring list, but I wanted to keep these examples short. So what happens if we apply head to IDs? We already know that the variables head and IDs will be instantiated here, but IDs type doesn't have quantifiers at the top level, so there's nothing to instantiate. So the a in head's type gets instantiated to list of polymorphic identity function. So effectively we're just removing the list constructor from the type of IDs. And as a return type we get the still polymorphic type of the identity function. My main point here is that we then don't fiddle with that type by trying to instantiate it, but we don't touch it at all. Or in other words, variables are the only places where we instantiate implicitly. But again, that's just what syntax-directed presentations of ML do. But that means that doing head IDs and then applying the result to 3 doesn't work. The result of head IDs is still polymorphic, there isn't an implicit instantiation going on, so we can't apply it to 3. Now if you do want to instantiate something, we can just use the one construct where instantiation does happen, and that's a variable. So we let bind a temporary variable to head IDs and then return that variable, but without freezing it. That means that this variable will then be instantiated. And again, because this explicit instantiation is nice to have, we added this as syntactic sugar, which is this add operator. Now in general, the first thing that happens is that the let binding may generalize the thing you wanted to have instantiated. So it may do a generalization that you didn't ask for, but it doesn't matter because we instantiate immediately afterwards. So from the outside, you just see the instantiation happening. Now one syntactic form that deserves special attention are let bindings. As we've already seen, let bindings implicitly generalize the values they bind, just as ML does. But there is an important difference. Let's look at this ML program here. We define ID as the identity function and then apply it to 3. The interesting part is that the ML type system allows generalization here, but it is non-deterministic about the type you give ID before you generalize. That means we can type ID with the polymorphic type that we've seen so many times now, but we can also give ID the type int to int. And if we choose int to int, there is nothing to generalize, and we don't need to instantiate later when we apply ID to 3. In ML, both of these typings work, and the non-determinism doesn't do harm. Now in FreezeML, things are a bit different. Let's define ID as before, but this time we apply the frozen version of ID to 3. Now if we pick the polymorphic for all A to A type for ID, this doesn't work, because then we need to instantiate ID before we can apply it, but the freezing prevents that. Now if we choose int to int as the type for ID, then suddenly this does work. That's because in this case, the freezing doesn't do anything. In other words, this means that the freezing makes this non-deterministic choice for the type of ID observable. And this is also a problem for type inference. Ideally, we would like to be able to just infer the principal type for ID, and that's it. But here we would have to detect that we have to pick a different type for ID. Now our solution is that when typing let x equal m in n, then we always enforce picking the principal type for m. That means that the example above doesn't actually type check in FreezeML, because we aren't allowed to give ID the type int to int anymore. This idea of forcing let bindings to yield only principal types isn't new. For example, HMF has done this in the past, but it is a deviation from what ML does. One thing I haven't really talked about so far are type annotations. FreezeML never infers polymorphic parameter types for lambdas. This isn't really a controversial choice. For example, HMF, FPH, and GI are doing the same. But it means that if you want to write a function that takes an argument with quantifiers anywhere in its type, you need an annotation. For example, this lambda here that expects a polymorphic function choose that returns either its first or second argument. But lambdas aren't the only place where we added type annotations. You can also annotate let bindings. One reason for doing so is if you want that variable you're binding to get a type that isn't the principal one. As we've seen on the previous slide, not using a type annotation would only ever get you the principal type. The other thing annotated let bindings are good for has to do with the order of quantifiers. I mentioned earlier that the order of quantifiers matters in FreezeML, just as it does in SystemF. So if you write an unannotated let binding, type variables are generalized in the order they appear in the type. But if you use a type annotation, you get to pick a different order. Now I want to talk about something that I hinted at a few times on earlier slides, and that's the large overlap between the typing rules of FreezeML and the typing rules of existing systems. I didn't show any typing rules of FreezeML, but there's a good reason why I didn't have to. If you're familiar with the typing rules of SystemF or a syntax-direct representation of ML, then you know most of the typing rules already. So let's go through them. And I should mention that our type system is syntax-directed, so these are all the syntactic constructs and at the same time also all the rules. The typing rule for frozen variables is actually just the typing rule for normal variables in SystemF. For variables that aren't frozen, you can use the variable rule from syntax-directed ML, which does the same kind of instantiation. You only have to change the rule so that the instantiation is allowed to be polymorphic. You can also take the rule for unannotated lambdas from ML. You only have to change it so that the return type is allowed to be polymorphic. As I said earlier, the parameter type must be monomorphic if there is no annotation, so that part stays the same. For annotated lambdas, you can take the SystemF rule in verbatim. The same is true for the application rule. We can just use the one from SystemF, or alternatively you can take the ML rule and allow polymorphic types everywhere. The only special rules are the ones for let bindings. For unannotated lets, I just showed you the principality constraint that we had to integrate. And we also had to take care of the value restriction in that rule, but let's not go into the details of that. Finally, annotated let bindings don't really have a counterpart in a kind of core language presentation of ML, so in a sense this rule is new. Let's have a high-level look at type inference. As we've seen so far, we carefully designed the type system so that it has principal types. So we took algorithm W, which is the original algorithm for Hintermühler type inference, and we only had to make relatively small changes. We distinguish between type variables and unification variables, and those unification variables stand for types that we don't know yet. Then it's important that for unification variables we track whether they can be polymorphic or just monomorphic, and that determines what types these variables can be unified with. There isn't really much more to say about type inference, but that's just because of how straightforward type inference turned out to be for our type system. And if you're curious about the smaller details, the paper has the full algorithm. Now I want to briefly talk about related work again, by talking about examples like single applied to ID again that I used earlier. So here's one attempt at categorizing this big alphabet soup of systems that I showed you earlier. There is one group of systems that use very expressive types. These types more or less allow you to defer certain decisions until a later point. For example, you may end up with a constraint in your type limiting how a certain type variable can be instantiated. Then there is a large group of systems that use heuristics to decide when to instantiate and when to generalize. I said a bit about this earlier, but in FreezeML we deliberately decided against doing that. Don't get me wrong, these systems have their merits and they will save you some ink as compared to FreezeML in many cases. But when they don't, the user has to understand what exactly the heuristics do in a case where they didn't do the right thing. So we made this deliberate decision of designing a system where we hope that it's that simple to understand what the type system is doing, even if you have to be more explicit about your intentions. And as a nice side effect, I've shown you how our typing rules are actually very close to both systemf and ML. For example, we don't need to consider n-array applications. Now there is a smaller group of systems that rely on such explicit decisions by the programmer, and that's the group that FreezeML belongs to. Now one thing that distinguishes FreezeML from virtually all of these systems is that they distinguish two different sorts of polymorphic types. They use ML type schemes on one hand and systemf-style polymorphic types on the other hand. You can then translate between these different sorts of polymorphism, but they are generally not directly compatible with each other. And as we've seen, FreezeML just uses plain systemf types. And of course the paper has a more detailed comparison with the other systems. Now some final words. Our design goals for FreezeML were to design a system that is simple to understand rather than trying to be very clever. And one way we think the simplicity manifests itself is by how close our typing rules are to ML and systemf typing rules. Keep in mind that we just had to add frozen variables and type annotations on binders to ML. This way we got the full expressive power of systemf, which is why we have translations back and forth between systemf and FreezeML. And finally, we implemented FreezeML in the Lynx programming language, which you can install via OPAM.